In this video, my good friend Craig Migliaccio comes out to our apprentice school up in Eustis at Lake Technical College and teaches a couple different classes, but one of them was a tour of the gas furnace in the classroom, just talking through all the components. It's a high efficiency gas furnace, so we don't work on a lot of them, so it's kind of new to some of us, but I really appreciated him taking the time. Find out more about Craig and all he has to offer at acservicetech.com.
So here you have a high efficiency gas furnace right here, and you can convert these from natural gas to propane and then back from propane to natural gas. So you buy these and they come as natural gas from the factory. If you were ever to change using the conversion kit from natural gas to propane, you're going to replace these springs right here. You're going to replace the two orifices here. There may be a plate here to adjust the combustion air, and then you're going to need to check your pressure coming in and going out, and you're going to need to adjust that for propane. So you know, natural gas, that runs at about 1/4 of a PSI. It's about 5 to 7 inch water column when it comes in, and propane will be around, say, 10 to 13 inch water column, depending on how high the pressure is adjusted on the regulator outside at the propane tank. This one, you can completely identify that this is a 2-speed gas furnace because there's 2 spring sets right here. And so if you ever see the spring inside, the real silvery one, that's for natural gas, and the whiter one, that's usually for propane, which is also referred to as LP. So right here, you have a flame rollout switch, and this is a manual reset. By the way, the power is off to this gas furnace. There's a button right here. If you ever need to reset that, that's usually due to a flame rollout where the flame is, say, licking backwards. It's coming back this way, and the flame is touching. There's a little bimetal disc that's in the front of this, and it triggers this little knob to set outright, and the only way to reset it doesn't manually reset like this one does back here. So this right here is a high temperature thermal limit switch, and this will automatically reset, and this temperature is taking right in the heat exchanger area. So that right there. And there's different versions of this depending on the model of furnace. This particular one looks like it just has the bimetal disc right at the opening. There's other ones that extend into the heat exchanger area, say that far or that far in there. There's also a fan control limit switch as well. But anyway, that's the norm right there. You have 3 pressure switches right here. And this, I was telling Brian, this is a real nice furnace to learn on, even though it's a high efficiency one. And the reason for that is right here, it says block drain on this pressure switch. Awesome. This one says high fire, and this one says low fire. They normally never say that. And so you have to kind of look at where the tubing is going in order to determine that as well. These have the inch water column measurements like 0.97 and 0.72. Well, what that's doing is that's measuring the negative water column pressure of the inducer motor while the inducer motor is running. This one right here has a tube going down into the collector box that's behind the inducer motor. So this is the inducer motor, and its job is to pull the combustion air from out here into this area, mix with the gas, and what's happening is it's pulling the exhaust through the whole heat exchanger, through the primary and the secondary heat exchanger, and then it's coming into the inducer motor and it's pushing out this way. And so if you have any condensation in a 90% efficient furnace, you have this tube where it's going to catch and it's going to go into your trap that's down here. Condensate, so water vapor is a byproduct of the combustion process, and so you're always going to have that. And that's how, this is I believe it's a 96% efficient furnace, but anything that's an 80% efficient furnace has a metal exhaust pipe, but anytime you have a 90% efficient furnace, it's gaining its extra 10% of efficiency, in this case 16% efficiency. It's gaining that from the heat exchange of the air, but mainly from the flame process. And so the secondary heat exchanger, you have water that's traveling through that heat exchanger, and you are able to transfer that heat that's still within the water as it's traveling through there. It's able to get moved basically into the air, and so the air is absorbing that heat from the condensate in the secondary heat exchanger.
So where's the secondary heat exchanger on this?
So the secondary heat exchanger is back in here. So it's right back here, where the primary heat exchanger is right about here. Primary heat exchanger is just a snake of maybe several turns, and then it turns into little tubes. Tube and fin, essentially, is the secondary heat exchanger. So what I was saying is a 80% efficient furnace doesn't have a secondary heat exchanger, because what happens is the exhaust temperature is much higher. And so what's happening is the condensate is not able to form, the water vapor is not able to condense, and it just goes right out the exhaust pipe on an 80% efficient furnace. 90% efficient furnace, you have a larger heat exchanger because you have the primary and the secondary. It's lowering the temperature of the exhaust so much that the water vapor turns into condensate back here, and it travels through that secondary heat exchanger and drains out right here, and it goes into this trap, this water trap, and then it comes out of the system over here. You have these pressure switches, like this one right here, is making sure that this trap is not clogged and that the water is not traveling up higher and higher and higher, because if the water backs up in the collector box, it can get into the inducer motor housing, which is right here, and the blades are going to start hitting the water in there. And so it's imperative that the condensate trap is not clogged. And so what you want to do is, if you ever need to blow this condensate trap out, you want to disconnect the pressure switches and take this tube off, and you can take some pressurized air and go through that. You can also fill it up with water, and you kind of have a hydraulic effect when you put just a little bit of pressure and blow it down through your condensate line, and that'll kind of clean out your condensate trap. You can't get into the condensate trap. It's all molded and it's got chambers in there, but the reason for the trap is the water height level. The weight of the water is able to allow the condensate to travel out of here, even though right above it is negative pressure from your inducer motor. So it's kind of the same premise as a trap on an air handler for air conditioning mode. The water weight is what allows the condensate to flow down the tubing. It's kind of the same principle. This inducer motor, its job is to push the exhaust out through, and anytime you're walking up to a furnace, you know immediately it's 90% or higher if it has a PVC exhaust. This PVC exhaust is basically the temperature of your skin. It can be 0 inches to combustibles where it exits the building at, whereas if it's metal and it's a B vent, it's normally around 1 inch to combustibles, such as wood, but you have to look at the ratings for that particular furnace, the temperature of the exhaust traveling through it. So you can't just say all B vent is that way, because there's newer types of B vent that you could use even on a wood stove, and it's much higher temperature. You have to have more clearance to the combustibles. Anyway, getting back to this, you have 3 pressure switches here, here, and here. We already said that this is a 2-speed furnace, so you have a high fire, so that's when the inducer motor is running at above 0.97 inch water column. So remember that. So right here, this inducer motor may be pulling 3-inch water column. So it's a very small amount of pressure. You also don't want to take these tubes and kind of suck on them with your mouth trying to get the pressure switch to trip. You can use a tool such as the SDMN6 from Fieldpiece. It has an internal pump. If you ever suspect a pressure switch as being bad, you can basically turn the power off to the furnace and isolate that switch and connect it to your pump. Read the pressure readings, and you can take these electrical connections off and use either a multimeter or the wires that come with that tool, and you can test the pressure switch individually. I used to be nervous about, oh, it could be the pressure switch, I'm not sure. It takes all of the guesswork out of it, and it's really nice to have that tool. But anyway, I'm not trying to pump that tool up or that manufacturer, but the reality is it's a fantastic design. Anyway, this one right here, if this trap clogged and the water level rose above this, then what's going to happen is it's going to shut off the negative pressure on this tube right here, and this pressure switch is going to open up. When this system is off, all of these pressure switches should be in the open position electrically. When you turn the power on to a furnace such as this right here, what it's going to do is it should be sending 24-volt power through all the safety switches, such as the flame rollout switch, the thermal limit. And on this one, there's actually 2 thermal limits on the sides of the blower motor, way back here and way back there. So you see these 2 wires right here, they're leading to a thermal limit switch. There's another one right back here. They're not doing much in a vertical position of a furnace. They would be doing their job if this was a downflow furnace, because what's going to happen is when the gas valve shuts off and the blower motor is still running, it needs to get rid of the heat that was developed by the combustion. And so you're going to have a blower off delay of maybe 90 or 120 seconds, and if for whatever reason it can't get rid of the heat and then it shuts off, then what's going to happen is those thermal limit switches are up top on the furnace and heat rises, right? So they would trip. And so if you're not supplying the correct amount of airflow or something like that, those would trip. So those are there. They should all be normally in the closed position at your standard indoor air temperatures. And you actually have a little scan on this particular one where you can take your phone and scan it. But a lot of them have their temperature limits on them where they open up at, and then it will be whatever it is minus a certain amount of 20 degrees or something like that, and that's when they would close back down again. Not on this one, but on the automatic ones. They're just an automatic bimetal disc. All right, getting back to all of this because I'm getting on a bunch of tangents. This is the PSC inducer motor. That's permanent split capacitor blower motor. So this capacitor, it's right there for you to see. So that's what gives it the artificial phase in order for the motor to start up and to continue to run efficiently. And you see that there's more than just two wires and a ground. You see it actually has a multitude of wires right here, but basically this inducer motor should be running in 2 speeds because this gas valve is running in 2 speeds, and you have high, medium, and common. You can potentially on this, I believe on this particular model gas valve, what's going to happen is you're going to get 24 volts between common and high with a multimeter if it's running in high speed. You're also going to get 24 volts when you read it with a multimeter, 1 probe in the medium speed and 1 in the common. So both, I believe on this particular one, you have to have both the medium and the high powered to be in high speed. For medium speed or just a single speed, low speed, you're just going to have power on the M right there. So you could potentially jump this into 2nd speed, but you can also wait for the furnace to ramp up to that additional speed. So if you set the thermostat up to a high temperature, it may want to run for maybe 15 minutes or something like that in the furnace. On the control board, this is called an integrated furnace control board, and so IFC. And what that does is it takes care of the combustion and the blower delays, and as well it has all of your switches, your adjustments for your blower speed and things on it, all integrated together. Back when on the old furnaces, you had a, say a fan limit control, or you had a ignition control module, and then you had a separate fan delay board, or you had on the fan limit control, you had the little bimetal, it turned, you ever see the dial and it turns the dial, and that's when it turns the blower motor on. So you have these older versions that are out there, and this basically combines everything all together on one board. This board uses flame rectification, which at any time when you turn the power on, there's a flame rod right back here. That should be live anytime the furnace is on, which means that if you put a probe on this tab right here, which goes to the flame rod, and you put one on ground or common, you should be reading anywhere from say 80 to 180 volts. A lot of times with these gas furnaces, it's right around 100 volts. And so that's alternating current. So basically you have alternating current ready at the end of that rod. And what's happening is when the gas is ignited, and the flame basically completes the circuit from the rod to the burner tube flame retention head. And what that does is that rectifies the alternating current, and it becomes direct current. And you can check for flame rectification by checking for microamps with your multimeter. So basically, and the power is off, but basically you would just disconnect right here and put 1 probe in here and 1 probe here. It's microamps, so it's very little. It goes through the meter and it's displayed on the meter. A lot of times it's 3 microamps, and that's once again is direct current.
And that is in series. You're wearing it in series, correct, yeah. And your meter has to have a microamp measurement scale. It's not milliamps. It's not the same thing. Microamps is a millionth of an amp, not a milliamp, which is a thousandth of an amp.
Yeah, I have a lot of times people trying to correct it and saying that it's supposed to be milliamps, and it's not. It's micro. As well, you have a silicon nitride hot surface igniter back here, and they are the newer version compared to the silicon carbide HSI, which is a hot surface igniter. That right there is going to last a lot longer. You're able to supply 120 volts to this particular one, and it turns orange basically, and that's what ignites the gas when you have this gas valve. Now, let me back up for a second, because this is a direct ignition gas valve, which means it's going to supply 24 volts say the common, and M for the low speed. It's going to supply the gas pressure. If it's natural gas, it'll be, say, 3.5-inch water column around there. And it's going to ignite, the hot surface igniter is going to ignite the gas, the flame. And then what's going to happen is that control board is going to be looking for the microamp signal. It's going to be looking for flame rectification in order to prove the flame. All that to say, this is a direct ignition gas valve, and if you ever see a small 1/4-inch aluminum tube coming off of this gas valve, that's called a pilot ignition. And so it ignites this little tiny pilot, and there may be flame rectification that occurs on this little tiny pilot, but guess what? It's only on one side, and so if you have 1, 2, 3, 4, 5, 4 burners or 5 burners, it's only really checking for flame rectification in one spot. Whereas direct ignition, you have the hot surface igniter on one side, or spark ignition, and you have the flame rod on the other side. There's rarely ever really an instance where you need to change out that flame rod. It's also called a flame sensor. It doesn't sense anything. All it is a stainless steel rod, and it has ceramic in order to isolate it from the ground circuit, because it doesn't want to touch the ground. That's all that is. I mean, there really is nothing to it. I can't believe how many flame rods are sold out there at flame sensors. It's crazy. Now, there are the small flame sensors on the pilot ignition gas valves, and they're real small, and those deteriorate over time or bend and just get out of whack. Yeah, you're going to need to replace those, especially on smart valve systems and stuff like that, where you have the HSI and the flame rod all as one pack, and you just replace that whole assembly. You can notice which pressure switches are for the high and low, just because it's attached to this inducer motor. And I know I covered this already, but this tube goes down to this lower part where the condensate is, and so that's how you can tell that is the one as a safety device to make sure that the condensate does not overflow. So if you are going to adjust the gas pressure, what you're going to do is you're going to take these screws off right here and here. If it was a sealed combustion, you'd want to take that door off as well, so you had the pressure that's in the room. Looks like that's going to be where your inlet gas pressure is going to be taken at. But basically what you're going to do is you're going to remove these brass plates right here, and inside there's a little plastic screw, and you're going to be adjusting the plastic piece that's inside of here with a flathead screwdriver. If you turn it clockwise, it's going to increase the pressure. If you turn it counterclockwise, it's going to come out and it's going to decrease the pressure. If you get this set up from natural gas from the get-go, you can do your combustion analysis, but usually it's set up pretty darn close to where it needs to be at. If you're setting this as a natural gas system, if you're doing propane, you absolutely need to adjust these, and you'll have a problem where the furnace isn't going to turn on unless you first initially tighten that plastic insert in the correct amount of turns inwards, just in order to get it close enough for it to fire correctly. Otherwise, you're not going to have enough gas pressure to ignite it properly, or it's going to ignite in a way where it could potentially pop this flame rollout switch right here. And just so you know, you should never be continuing to reset a flame rollout switch. There's a problem. And it doesn't necessarily mean it is a cracked heat exchanger right away. It could be that the heat exchanger or this plate right here is pulled away from the heat exchanger. There's a multitude of things, but basically you have the air from the blower motor is somehow pushing the flame back to the flame rollout switch. That's really what the problem is. A lot of times it is the crack in the heat exchanger. It may not show up until the heat exchanger is hot and the crack opens up. And then, so the crack may open up, and then you have the blower air enters in because it's entering into the lower pressure area and then pushing the flames back out. So if anytime that you're watching this operate, and then all of a sudden you hear the blower motor turn on, and then you see the flames start flickering around, that's an indication that you probably have a cracked heat exchanger, and then you got to do more testing from there, such as turn this off and take out this thermal limit right here, and take a camera in there and see if you can see where the crack is. You can potentially get to it from up above it, up here in the evaporator coil area. You can also take carbon monoxide readings at the supply registers while it's running. But basically, you want to be able to give the customer confidence that you did find the crack in the heat exchanger, and because there's a lot of people out there that want to sell a new furnace, you don't want to be somebody that's guessing. You want to be able to try your best, if possible, to confirm that. And once again, if you're reading high levels of carbon monoxide at the supply registers, that's a pure indication, hey, you have carbon monoxide issues because the flame is burning improperly and it's getting into the conditioned air within the building.
When you have a primary and secondary heat exchanger, it's because when I first heard this, Like, because again, I don't work on high efficiency gas, and so I would assume, as somebody who doesn't see them all the time,
yeah, the differential in the temperature.
Yeah, I would assume that you would have your primary heat exchanger, and then you'd have your secondary heat exchanger, but that isn't why, because where's the cooler air?
Right.
The cooler air is at the bottom, and which one is the cooler coil? The secondary heat exchanger, right? Your secondary heat exchanger, you're extracting that last little bit of heat out. So the air goes over the secondary first before it goes over the hotter primary heat exchanger because of that air temperature differential.
Say right there, it makes perfect sense once he started asking it, and you have a, you have a little bit to think about, and you're like, aha.
Very well,
no, you're right. That's great. So that's really what it is. It's the temperature differential, to try to absorb as much heat as possible out of that condensate. Great. Awesome.
Talk a little bit about the intake that you'd normally have in a high efficiency.
So what I would normally do is I would never really, me personally, leave this blank. I would run this to the outdoor air because I don't want the inside of the building to turn it into a vacuum, because that's what's going to happen. It has to draw its combustion air through here into the combustion chamber, which is located right here. So I would always run that out. Me personally, I like to go into a concentric kit, so there's one hole out of the building instead of two. And it just makes for a nice, neat installation, whether that concentric kit goes out through an exterior sidewall or through the roof.
Yeah, and concentric kit is just it's just a tube within a tube. So you have a tube in the outside and then a smaller tube in the inside, and that's how, so that way you don't have to make two penetrations, one for intake, one for outlet.
The control board is a smart thing right here. So even though this is 2-speed, we wouldn't have 2 speeds at the thermostat up here if it's a basic thermostat. I'm not talking about the communicating ones and all that, and they're not even called thermostats and the interfaces and things. But anyway, so down here you just have one W wire, and that's your heat wire. So as soon as you're sending a signal from the thermostat to the letter terminal W, so you got to remember that your thermostat acts as a switch. So when you turn heat on, what's going to happen is R and W touch. It does not turn, the thermostat does not touch R and G. It does not turn the fan on. The control board tells when the fan is going to turn on based on the sequence of operation for heat, which I can just run you through that quickly. What happens first is you're on a call for heat. What's going to already happen is the control board is already monitoring all the safeties, and if any of those safeties are open, such as the thermal limits, then it's going to either run the fan, or depending on if it's a cracked heat exchanger, it may run the inducer motor, but usually it's running the fan. And it may have an error code. There's an LED status code, so if you're not sure how to recall the status code, you want to look through the window first before taking the door off and count the status codes, whether it's a short flash, long flash, or a combination of both, depending on the unit. You want to write that down before taking the door off. You can recall the status codes of all the errors that have occurred on the gas furnace. You just got to read the manufacturer's literature on how to recall it. So anyway, on a call for heat, R and W touch, and so once you have 24 volts on the W here, it starts the sequence of operation for heat, where you have the inducer motor turns on first, and then the pressure switch is closed, at least, so say it's in low speed, this switch and the low speed switch are going to close. This one may still be open, but it's probably going to close as well, because the inducer motor pressure is going to be higher than these. It's not going to be closed. It's going to be a significant amount higher. So first step, inducer motor turns on, pressure switch closes, hot surface igniter turns cherry red. Then after that's cherry red, then what's going to happen is the gas valve is going to send the full gas flow through. So the fourth step is the gas valve. Then you have your ignition. So step 5, you have your flame rectification process is proving the flame. Then 6 is the blower on delay. So the control board is going to wait for the primary and secondary heat exchangers to heat up, so you're not blowing low temperature air in the building. And then after the blower on delay, you have the control board turns the blower motor on. Now in this case, you have a variable speed ECM motor. Some of these have a multi-speed ECM motor. This is a ECM variable speed. It looks like a newer version of the 3.0, or it might be a different manufacturer. I'm not sure, depending on, the plug looks a little different than what I'm used to seeing. Anyway, so this is a variable speed and blower motor right here, and this is a PSC inducer motor. So the control board is going to be able to get the extra efficiency. So say the 90% efficient to the 96% efficient, it's kind of getting that out of the ECM blower motor and the airflow. So the heat exchange between the primary and secondary heat exchanger and the variable speed blower motor. So I call it 7-step sequence of operation. Some people call it 6-step. You kind of just make up your own thing. Once you're comfortable with that, you just teach that. On these IFC, so the integrated furnace control, a lot of times you have a tab there for the EAC, which is the electronic air cleaner, and also the humidifier. In this case, you have a bypass humidifier, which are preferable. I've seen other humidifiers that's actually taking air from the attic and pushing it into the duct, like all kinds of nonsense, you know, it's crazy. But anyway, the newer integrated furnace control boards have a 24 volt for the humidifier and a 120 volt for the EAC. These indoor gas furnaces are typically single phase 120 volt. If you have an outdoor package unit, the package units cannot be any higher than 80% efficient because you'll have a condensate line on them, and obviously it's low temperature outside, so that condensate line would freeze. So those ones are basically stuck at 80. You may have in your service truck a multi-tap transformer that's good for 240 volts, 208, 120. It's got multiple leads on that for the input, the alternating current, and on the other side you have 24 volts, which anytime you measure between R and C, after the power goes through the fuse, there's usually a 3 amp or 5 amp fuse. In this case, once again, the power is off. You have a 3 amp fuse right here. The power is going to go from the hot of the transformer. It's going to go into the control board. It's going to go through the fuse, and then from there, it's going to go to power your status light, and then also going to go to the R terminal. You can measure it with a multimeter between R and C just for main power. And 24 volt will measure anywhere from, say, 24.5 volts to 29.5 volts. That's usually around what it is. This is high voltage, and this is low voltage, 24 volts. 24 volts is your control voltage, and it also powers devices, you know, on your gas furnace. Anytime you see a black box on the control board, that's usually a relay. Those are typically a DC relay instead of AC, that when they're mounted, soldered on the control board. Transformers are always alternating current in, alternating current out. They do not rectify.
That's why the doors usually have louvers on them.
Oh, if this was in a closet?
Yeah.
Yes.
So it doesn't create that negative pressure in there,
right,
which then would kill the flame.
Yes. It's gonna. Yeah, if you don't have good combustion air, the flame is not gonna be efficient. It's not gonna work really well. But it will get that. It will turn that into negative pressure, and it will pull it from outside somewheres. It will steal it from somewheres through a crack in the recessed ceiling light or whatever from the attic. There's going to be somewheres where it's going to pull air from. But the nice thing is, though, a garage is usually separated from your living area by a sealed door that is usually fire rated. But
you don't want to have a case where a flame is starving for oxygen, because it can start to burn improperly. And that's when in 80% we talk a lot about the combustion air zone, which is the zone around the furnace, and we've talked about, like, if you have water heaters or other things in there, you may not have an issue with backdrafting on your furnace, but if you negatively pressurize the combustion air zone, you could backdraft a water heater that's in that same space, or, you know, other gas appliances potentially.
That's huge. You know, that's the big thing when you have a water heater there. Yeah. There's also what's called orphaning. What is it? Orphaning the water heater. It's basically you have a large exhaust pipe. And so basically you had maybe a boiler or an old gas furnace going up into a shared exhaust with a water heater, and the water heater has a small exhaust pipe. And so what happens is then you upgrade to a higher efficiency gas furnace, and you're left with this large exhaust pipe. And what happens is there's not enough heat from the water heater for the combustion air to rise. Eventually what happens is it's just not hot enough, and then it comes back down through the natural draft air intake back into the room, and now you have carbon monoxide in the building. So if you were going to orphan the water heater, you are going to need to rerun the exhaust pipe, and you can run new through the old piping and just run 3-inch instead, but you're going to have a new termination. So basically up on the roof, you would have to put a new flange that's smaller, and that's kind of hard too, because you have this large hole, and then you got a new flange. It's only like 1.5 inches on both sides bigger than the actual hole. Realize also on a water heater, you do have cold air rising and mixing with the exhaust gas, and that's actually supposed to slow down the exhaust from rising too quickly as well. You know, you have a baffle in a standard natural draft water heater where you have the exhaust is naturally draft. You have a baffle that kind of tries to but slow down the combustion, the exhaust from rising too quickly. And then you have the cold air that comes in as well, and that's also there to slow down the exhaust. Otherwise, it's just going to skyrocket right through that without the heat exchange from the exhaust to the water jacket that's surrounding it. That's the premise, I guess, of the old natural draft boilers, water heaters.
Do you want to mention anything about the way that the gas is piped on this for anyone who's going to comment on it and hammer it?
So two things. One being that this is just a training unit, but you should have a off valve right here. And so basically there's several things. You want to have an off valve, and you're going to have a drip tee. And this is kind of an odd setup for the drip tee. Usually people that really take pride in the installation a lot of times don't use a coupling. Now that may hurt somebody's feelings or whatever, but you know, you can use.
Is it better to have a check valve on there instead of like a regular ball valve too?
You mean in case the gas lets loose or breaks off or something like that? You might want to have that upstream. It depends, because a lot of times you want to have hard pipe to the outside of the furnace if you're going to have a flex line, if that's what you're referring to. So you have a flex line from here over. Anytime you have a flex line going through the cabinet, that's not a good thing either, because that can vibrate and rub up against the metal and then chafe it, and then that could result to a leak. But yeah, there's new valves and also just flare connections that are supposed to stop the gas flow if it breaks off. And another thing which I was kind of surprised, this is what I have at home, is galvanized piping, Schedule 40 piping that's galvanized. And I get a lot of comments, why are you using that? You're not allowed to use that. Well, guess what? The International Fuel Gas Code is what everybody follows, and it doesn't say anything that I'm aware of about galvanized versus black iron. Now, the supply houses near me only sell galvanized, and that's because I live by the shore. So the ocean's on one side, the bay's on the other side. If you have black iron running outside, it's going to eventually rot and leak. And so the inspectors take it upon themselves to say, no, I want galvanized there, not black iron. There's no problem with running galvanized that I'm aware of at all. All of the gas line stuff and then in the combustion air stuff that he's talking about is all in that International Fuel Gas Code book, and the newest update will be 2021 on that, but we're still using 2018 version. So for all your sizing of the gas lines and stuff like that. So you're going to size your gas line for the amount of BTUs of the furnace, and you're going to have to reduce down once you get to the furnace, because you normally have 1/2 inch coming in. Larger package units will have 3/4 or even 1 inch, or depending on whatever the BTU
Also, when
size.
you pipe those together, it's also a good idea to use some type of thread compound versus just tape.
Yes. There are some type of like Teflon tapes that are rated for fuel gas, but typically we use we call it pipe dope or thread sealant. This one's a Teflon based one. Absolutely have to use your thread sealant on all the threads, and that seals in the joint. This is not like a flare connection. These are the threads literally hold in the pressure, whereas a flare face is matted up against the flare adapter, and that's what seals in the pressure, not the threads on a flare adapter. Kind of like that one right there. You don't want to put any thread sealant on the flare face or on the flare threads, because that potentially could dry out over time, and then you have a possible leak point. But the actual, on a gas line, because it's a lower pressure than refrigerant, so like a R410A mini split, we usually put, or at least I usually put, a refrigerant oil or nylog on the flare face and then tighten that in. On a gas line, I typically don't put anything on that, and like I said, for propane, it's 10 to 13 inch water column, which is about half of 27.6 inch water column. 27.6 inch water column is about 1 PSI. All that to say, propane's about half a PSI, natural gas is about 1/4 of a PSI, because natural gas runs about 5 to 7 inch water column. Commercial sites, you might see them increasing it to 8 inch water column or something like that, because of the gas lines weren't sized properly or something to begin with, so you run into that as well. But this regulator, even if it's 8 inch water column or 6 inch water column, will still reduce it down to whatever the 3.5 inch. That's not to say that you shouldn't check it again if they were to make a regulator adjustment at the outdoor regulator, but they do have a variety of input water column for gas. And it's inches of water column. So anytime you see WC, that's different than on a recovery tank where it's, your water capacity.
Big thanks to Craig for coming out to the class and sharing so much of his knowledge. Please go to acservicetech.com to find out more of what he has to offer, including his book and his 1,000-question workbook, both excellent resources. He's got a lot of great stuff there. That's acservicetech.com. Thanks, Craig.
Thanks for watching our video. If you enjoyed it and got something out of it, if you wouldn't mind hitting the thumbs up button to like the video, subscribe to the channel, and click the notifications bell to be notified when new videos come out. HVAC School is far more than a YouTube channel. You can find out more by going to hvacrschool.com, which is our website and hub for all of our content, including tech tips, videos, podcasts, and so much more. You can also subscribe to the podcast on any podcast app of your choosing. You can also join our Facebook group if you want to weigh in on the conversation yourself. Thanks again for watching.